Hello, my name is René Raffray. I'm the ITER blanket section leader, and I'm the blanket integrated product team leader. And I'm going to make this talk, which aim to introduce the functions, design, and operation of the ITER fusion blanket to newcomers. First, what is a fusion reactor blanket? What image comes to mind when you think of a blanket? You think about cover, protection, warmth, maybe a cozy feeling. All of these are applicable to a fusion blanket, except perhaps for the cozy feeling. The blanket system surrounds the fusion plasma and blankets the outer component. Let's have a little recap about the fusion process and magnetic confinement to introduce the blanket and its functions. As you may know or recall, the fusion reaction is basically the reaction of two heavy hydrogen isotopes, deuterium and tritium, which combine together to create a neutron and a helium atom or an alpha particle. But in order for this fusion reaction to occur, we need to heat the fusion fuel to very high temperature, about 150 million degrees C, to create the conditions for fusion. At these temperatures, a plasma is formed with the electrons separated from the nucleus. To maintain such a hot plasma and prevent it from touching the walls, a magnetic field cage is formed to confine the plasma particles within a donut shape. These high magnetic fields are produced by toroidal coils, shown in blue here, and poloidal coils, shown in gray, which need to use superconductors to avoid drawing large currents through an electrical resistance. These superconductors are cooled by liquid helium at 4 degrees absolute, 4 degrees Kelvin, or minus 269 degrees Celsius, to keep them at a sufficiently low temperature for them to have basically no electrical resistance. So in a tokamak reactor, you have a plasma shown here in yellow, which is going to be at a very high temperature, 150 million degrees C. This is about 10 times the temperature of the core of the sun. A little bit further, you're going to have the toroidal field coils, shown in blue here, which are cooled by liquid helium at 4 degrees Kelvin. 4 degrees Kelvin, to give you an idea, this is the background temperature of space. And these two extremes of temperatures are separated by a few meters. This is really an astounding temperature gradient. And it's hard to imagine that such a temperature gradient could occur anywhere in the universe. And what do you find right in the middle of these two extremes? The blanket, shown here in gray. Let's look now at the main functions of a fusion blanket. The first function is to provide shielding to reduce the heat and neutron loads in the vacuum vessel and ex-vessel components behind the blanket. As I said earlier, you have the fusion reaction, and out of the fusion reaction, 80% of the energy produced is carried by a neutron and the rest by the helium atom or the alpha particle. These highly energetic neutrons are neutral and cannot be controlled by either a magnetic field or an electric field, and they go wherever they want. So how do we deal with these pesky neutrons, which seem to have a mind of their own regarding where they're going? We just blanket them. So the energy from these neutrons are transferred to the structure around the plasma, mostly to the blanket, before they reach the outer components, the vacuum vessel and superconducting coils and other components. Just to give you an idea of the energy of this neutron, a 14.1 MeV neutron, if there was nothing to stop it, if it was moving in empty space, it would reach the moon in about 8 seconds. And the distance from the Earth to the moon is about 380,000 kilometers. Another function of the blanket system is to absorb the radiative and particle heat fluxes from the plasma. 20% of the fusion energy is carried by the so-called alpha particles, the helium atom. These energy are deposited as radiative heat and particle fluxes on plasma-facing components, the blanket first wall, and at the bottom, the diverter. The split between the energy deposited on the blanket and in the diverter depends on the plasma scenario and the phase. So the blanket first wall then has to be designed to accommodate such particle surface heat fluxes, which are typically of the order of 1 megawatt per meter square for ITER. Another function of a blanket is to provide a plasma-facing surface which is designed for a low influx of impurities to the plasma. So producing and maintaining a plasma requires heating a gas to a very high temperature, as we just said. Electromagnetic radiation by electron impacting on impurities in the plasma is a large energy loss mechanism that cools down the plasma and makes it basically quenches the plasma, and the reaction will stop. So to keep the plasma hot, we need to minimize the impurities from the plasma-facing components and the radiation losses. Typically, these radiation losses are proportional to the square of the atomic number of the impurity. The atomic number is the number of protons in the nucleus. It's called Z. So we have selected for the ITER blanket first wall an armor which is a very low Z material, which is that's plasma friendly. This is beryllium. Beryllium has an atomic number of 4. Another function is to provide limiting surfaces that define the plasma boundary during startup and shutdown. To start up the plasma and eventually the reaction, the plasma starts in a circular limiter configuration, as you can see. Typically, it touches the first wall at the inboard, and then it grows and gradually changes the shape to have the more traditional D shape, and then switches to what we call a diverter configuration with an X point form at the bottom near the diverter. The high resulting heat flux on the first wall during startup and also shutdown. Shutdown is the reverse process. This is a key factor in designing the first wall. The blanket system also provides passage for and accommodates requirements of interfacing systems, in particular of plasma diagnostics. ITER, as an experimental device, includes an array of diagnostic systems, about 50 of them. This is for machine protection, for plasma control, for understanding the physics of burning plasma. And most of these diagnostic systems interface with the blanket to access the plasma, including in the case of ITER, all that is listed, all these diagnostic systems listed here, such as neutron activation lines, bolometers, Rogowski coils, etc. And even in post-ITER reactors, for demonstration reactor or commercial reactor, you also need a number of essential diagnostic systems. Another very important function of a blanket system is to breed tritium to achieve tritium self-sufficiency. As you know, tritium is one of the fuels to produce fusion. It fuses with the deuterium to produce a neutron and a helium atom. But deuterium is readily available from seawater, but tritium is not, and is also expensive to purchase. So tritium breeding is essential for a fusion power plant. And how do we do that? We introduce lithium in the blanket, which will react with a neutron formed by the fusion reaction to produce tritium. Now, not all neutrons from the fusion reaction will be captured by the lithium, and the blanket then needs to have a neutron multiplier, such as beryllium or lead, which basically react with one neutron and produces 2. So you multiply the number of neutrons, and then you can multiply the reaction of lithium and a neutron to produce tritium. And in so doing, the neutron energy deposited in the blanket is also enhanced, typically by a factor of 1.2 or 1.4. And finally, another main function of a blanket system is to remove the energy deposition with high quality for effective power generation. This means that we need higher temperature coolant, materials that can accommodate this higher temperature, and this allows to have a higher power cycle efficiency, typically a Rankine cycle for a water coolant, or a Brayton cycle for helium-cooled blanket. As an example here, you can see a Brayton cycle where typically you can see the compressors and the turbine, which are used then to generate electricity. So the material and design that can accommodate these temperatures, and also higher neutron fluences. Higher neutron fluences means that the component can stay longer in the reactor, given the neutron flux from the reaction, which means that you have a longer lifetime. So both the longer lifetime and the high temperature operation affect the economics and attractiveness of a fusion power plant.